In maritime navigation, air travel, and road cargo, a crosswind is never a good thing, right? But here, we're going to make an exception. My name is Christoph, and I welcome you to my videos on technological mitigation of respiratory diseases. If you happen to be desperately anxious about your family member in long-term care contracting COVID-19 and want to alleviate your hopelessness, waiting for institutions and governments to act, you've come to the right place. There is something easy and very helpful you can take control over and do yourself right now. It is clear that although vaccines are beginning to roll out, and that's great news of course, with the emergence of highly transmissive, more deadly variants and doubts about vaccine efficacy against them, the situation in long-term care remains tragic and concerning. This is especially unsettling if you are in a developing country where unfortunately you could be near the end of the vaccine line and may not get a steady stream of doses for a long time. In my opinion, it is high time we bring on board some innovative assistance from other disciplines, so count me in. Today, my engineering contribution is to explore the role of aerosol transmission in long-term care with you, and to show you how to build an apparatus costing less than $100 and a half day's work with basic tools that aggressively attacks the transmission problem at its source. The simple but elegant and employee-safe solution immediately increases protection of your family member in a big way, quickly and effectively from one day to the next. My calculations show that if every room in your building installs this piece of equipment and employees follow trivial operating guidelines, the efficacy of your building can reach an improvement as high as 99.93% in reducing your present regional case statistic for long-term care, regardless what it is, reasonably good or very bad. Even one life alone, that of your loved one, is worth the effort. Without exaggeration, its mitigation performance can be over 100-fold better than a completed 2-dose regime of an mRNA vaccine. If you've stayed tuned this far, I think you might like this. So let's get started. We need to first identify the primary source of the problem. So let us examine the worst-case transmission scenario, which everyone knows to be a sneeze, with the best possible outcome. Looking from the top view, you are the healthy person in green, and I am the infected one in red, half a meter away from you, violating the 2-meter rule as happens regularly in long-term care centers. Neither of us is wearing a mask. I sneeze. All my particles are projected out at 50 meters per second. You take one breath and you're infected. Let us now backtrack and interpose a barrier that is different from plexiglass but accomplishes the same thing. So taking a sledgehammer to a thumbtack, we interject the hot exhaust of a jet aircraft engine at a wicked speed of 300 meters per second. I sneeze again, and clearly you do not need to be a physicist to see what happens, that you are now safe, you don't get infected even though we are not wearing masks. Even if you go downstream to the end of the runway, you won't get infected. So we see that the jet exhaust accomplishes two things. It deflects the particles and it eliminates them by burning them to a crisp. Okay, let's figure out if we can transfer these two ideas into something more practical. Here is a laboratory simulation of a sneeze through a mask. The sneeze cloud in green has traveled approximately 3/4 of a meter in 1.5 seconds. For our next experiment, we want to know how long it takes the sneeze cloud to travel 0.4 of a meter. It turns out that a projected gas particle cloud, expanding and deforming as it moves, falls in the realm of what's called chaotic behavior in classical mechanics. To simplify, here I applied simple deceleration to arrive at a value of approximately 1 second. Let us now tame the previous experiment to bring it more in line with a typical resident's room. However, we are still sticking with the sneeze. Here, I put on a mask while you remain without a mask. I sneeze again. The 3 red arrows show you the position of the 1/4 meter wide sneeze cloud after 1 second. So the question to answer is, what is the speed of a crosswind needed to deflect those particles away from your face in time so that you do not get infected? The answer is 1 meter per second. Therefore, 1.5 seconds following my sneeze, the infectious particles will be pushed off to your left and not hit you in the face. So it is easy to see that a 1 meter per second crosswind will prevent infection even though you're so close to me, although it does look to be just borderline effective. Of course, a sneeze is an abnormal condition, so if you are thinking ahead that attendants don't normally sneeze at their residents even through their masks, but rather talk to them, you are on the right track. These two laboratory experiments tell us something quite interesting. Attendants should be aware that even when using crosswind deflection while wearing a mask, they should turn away from the resident in order to sneeze or cough. To avoid fomic transmission, it is better not to cover one's mouth when sneezing. However, to maintain the high efficacy of this solution, momentarily facing in the same direction as the crosswind is blowing is mandatory. So now, when I am breathing and talking, my aerosol cloud is traveling much slower and can be easily deflected by a 1 meter per second crosswind, and you are safe. Therefore, it is deflection that is the first and by far the most important line of defense. However, because we don't have the heat of a jet exhaust to annihilate these infectious particles, they are eventually dispersed into the entire room volume and can cause latent infection hours after the infected attendant had left the room, although the probability is substantially smaller than in the initial close interaction. Let us stay with this view and use our imagination for a few moments. The key aspect to recognize is that the condition created after deflection you see here is similar but in fact much less dangerous than another condition created when an infected attendant enters a room and then talks without any close contact with her resident, thereby leaving latent aerosol particles in the room which then spread into the room volume by normal diffusion and natural mild turbulence. So if the crosswind solution is used even in the second situation, it turns out that the increased wind turbulence greatly accelerates the dispersion of particles throughout the room volume, thinning out dangerous localized clouds at a much faster rate, immediately reducing more infectious concentrations in those areas where the infected person passed. You can see this effect in a computer animation in video part 2. It is easy to conclude that you are safe from close contact infection. However, how can you be protected against latent infection, although greatly diluted, that has nonetheless spread into the room volume? Let us see. Instead of a hot jet exhaust, let's use an air filter. Now that the crosswind is continuously scrubbed, sinking infectious particles, it acts as a clean air source to keep you safe from latent aerosol infection, providing your second line of defense. To handle normal talking particles that escape through a mask, obviously, a fan is a good place to start. This $40 box fan has 3 speeds, but as is, it will not solve the infection problem. Why? When you turn this fan on, you get an exit pattern that looks like this. We need to modify it according to the needs of the environment and the requirements needed to achieve the desired objectives. A key consideration is that the apparatus itself should not get in the way of a worker-resident interaction. That means it has to deliver the required crosswind velocity of at least 1 meter per second at a distance far away enough so that it does not interfere with normal work. Because a stock fan has a wide emission pattern that causes exit velocity to drop off quickly, we have to adapt an airflow concentrator that works something like a fire hose nozzle used to form a strong, narrow beam of water. To show you how that is done and how infectious particles get eliminated, let us see a photo of the completed assembly. This unit you see here has been in operation in my mother's room since the beginning of November 2020, and she did very well despite a major outbreak in her residence. This seemingly low-tech but life-saving device that you can build from readily available materials consists of 6 main components: an air purification filter, a simple box fan, a baffle, an airflow concentrator, the tilt angle, and 6, the most important component that you don't see, a simple protocol that healthcare attendants need to follow. You could rightfully think, well, isn't this gadget just a fancy air purifier? The answer will become apparent that it is a small yes, but also a big no. Now, if we take the stock fan and attach a filter stack to the back, the exit port shrinks and the pattern you saw last time becomes wider instead of narrower, A second side effect of attaching the filters is that we get negative pressure zones in the corners of the exit area. These negative zones create a recirculation of frontal infected air, which of course is not desirable. So we solved the recirculation problem by installing a simple baffle. The optimum diameter of the baffle where the corner negative pressure zones transition into positive zones is 38 centimeters for this filter combination and family type, thereby defining the diameter of our exit port. To build the airflow concentrator, we use a circular arrangement of toilet paper cores to create a laminar airflow. When we turn the fan on, the air stop in the center creates a negative pressure zone that draws the outside positive zones inwards, creating a narrow beam of air. All that results in a crosswind air barrier that is only a half-meter diameter at 2.5 meters away from the assembly. So now, let us see how all this works. Potentially contaminated air enters through the back of the device, passing through the filter at a velocity of a half meter per second. The air is then purified and comes out as a narrow beam at a velocity of 1 meter per second. Recall that the second feature of the jet aircraft exhaust was burning the viral particles. So to eliminate infectious particles in the residence room, we use filters to achieve a similar objective by cycling the contaminated air in the room through the filter stack, eventually scrubbing the entire room volume to a high degree of air purity. With the speed control, we can set the crosswind velocity to 1 meter per second, 2 meters per second, or 3 meters per second. It is easy to imagine that instead of a sneeze for normal loud speech through a surgical mask, a 1 meter per second crosswind will be sufficient to mitigate any potentially infectious aerosol clouds emitted by an attendant, even if the attendant is only 30 centimeters away from his resident. For any face-to-face interactions closer than 30 centimeters, such as a toileting operation, setting the crosswind speed to at least 2 meters per second is advisable. So let's now go to my living room and build a unit. you.